This is a result of Petrashku from 2008. I'm not going to go into how it's done, but if you're interested, it's a little bit less. It would be nice to do better, but my guess is there should be a lower bound that with constant, so this is for any constant k. It would be nice to do better, like a square root of n or something, but my guess is there's a matching lower bound. I don't think that's known. Okay, so that was rank. Our next challenge is to do select, the inverse. And select is a little bit harder, I would say. Don't have a great intuition why, but it is. And we're going to be able to use the same kind of technique. So again, we can use a lookup table, and so I'm going to do that first. So just like before, if we have bit strings of length at most half log n, then we're only going to need something like root n space. It's root n, again, times log n, log n space. Because just like rank, there are at most n possible queries, actually fewer because there may be fewer 1 bits, but at most there are n 1 bits to query. An answer is now an index, which is within a thing of size half log n. So I just have to write down an index of that size, so it's log n bits to write it down. Cool. So that's the same. Now the challenge is about getting down to half log n bits. We're going to use the same technique of 2 levels of indirection, but they work differently. There's an extra thing we need to deal with in select. There will be 2 cases depending on whether your array has lots of 1s or not so many 1s. And those 2 cases can vary throughout the string. So what we do, first of all, is so maybe I'll go over here. I'll stick here, whatever. So we're back to an n-bit string. So we're looking at, we want the analog of this structure of chunks. Now we can't just say, oh, take the bit string, divide it into chunks of equal size, because then given a query, we want to do select of j. We need to know where which of these chunks j belongs to. So instead of making them equal size, we're going to make them have an equal number of 1 bits. So then we can just take j, divide by the size of these chunks, which is log n, log n. You could probably do log squared as well, but log n will is a slightly better choice. And so we just divide every log n 1 bit, put a vertical bar. That way, given j, we divide by this thing, take floor. That tells us which chunk we belong to. Okay, so it's different, decomposing by 1 space instead of 0, 1 space. And so for those guys, we just store an array. If your query happens to have is 0 mod this, then you have your answer. Otherwise, you still need to query within the chunk. In some sense, the array has gotten divided something like this. So the number of 1 bits in here is always the same. Log n, log n, 1s. Okay, so you can now teleport to the appropriate chunk, and the issue is how do I solve a chunk? But now chunks have different sizes, which is kind of annoying. That's why we need this extra step, which is within a group of log n, log n, 1 bits. I'm calling them groups now instead of chunks. So each of these groups has different size. Let's suppose it has size r. So let's say it's r bits long. Okay, r is going to be different for each chunk, but we'll do this for every chunk, every group. Then there's two cases. If r is big, we're done. How big? Well, if it's at least the square of the number of 1 bits, that means it's very sparse. Only square root of the bits are 1s, the rest are all 0s. Then I can afford to just store all the answers. I'm just going to store a lookup table of all the answers if it's very sparse, because then I claim I only need this many bits in order to store all of these answers. So if I do this for all groups that have a large number of bits, I store this lookup array. How many, if I sum up the sizes of all these arrays, how much do I pay? Well, the lookup array has this kind of size. They're log n, log n 1 bits, and each of them I need to store an index for them. Now this could cost log n bits because potentially one of these groups is very large. It could be almost linear size. So I need log n bits to write down a position in there. There's log n 1 bits to write down a position for. So this is the size of one of these arrays. Now how many of these could I possibly need to store? Well, I know that this group has log n squared bits in it. So the maximum number of such groups is n over that. N over log n squared. And now we get to do some cancellation. So this 2 cancels with this log n, and then this log n cancels with this log n, and so we get n over log n bits, which is slightly little o of n. Okay, again, it is possible to get n over log to the k space, but we won't do that here. We'll be happy enough with n over log n. Okay, but we're not done, unfortunately. So we've reduced into groups, and I've only given you one case. This is when r is large. The other case is r is small, meaning the number of bits in the group is at most log n squared. That's a good case for us because that's pretty similar to rank. Here we got chunks of size log squared. Here it's slightly larger than log squared, but only by a polylog factor. And that would correspond to this step 2 in rank. If you do step 2 and step 3 here, then we get step 2 of rank. We've reduced to polylog size chunks by getting rid of this case. And so we have to do it again because we have polylog size groups, but we need to get down to groups of size log, half log. So we need to do another layer of indirection. So we get to do steps 2 and 3 again. This is what I'll call step 4. Repeat steps 2 and 3 on, sorry, I didn't say, I need an else clause. Else, I'm going to call this bit vector a reduced bit vector. So I've reduced to order log n, log n squared bits. And so step 4 is on all reduced strings, all reduced bit strings. I want to do steps 2 and 3 again. Let me do it quickly. My goal is to further reduce to poly log log n. Right? I took n bit strings and I got down to poly log bits. I do it again, I should get down to poly log log bits, and indeed I can. And this is plenty small. Poly log log, it's way smaller than half log. So we don't even need that much of the lookup table. Fine. So I'll call this 2 prime. I want to make this explicit because they are slightly different. Because now everything's relative to this, or to the reduced string, which is polylog. This gets hard to pronounce, but every log n squareth 1 bit, we're going to write down the relative index within the reduced string of size log n. So writing down the relative index only costs log n bits. Because we're in something of size log n, so writing down that index is short. We write it down for all of these, so we end up paying n over log n squared. That's the maximum number of these indices that we need to store. Each of them we pay log n. So here I'm summing over all the reduced bit strings. This is an overall size. It's at most n over log n squared that we need to store. Could be fewer if there aren't many reduced bit strings. But worst case, everything ends up being reduced. So we have this many times that many bits, and we get n over log n bits. Okay, this is roughly following the pattern of step 2 over here. Step 2 over here didn't just have the log term, it also had an auxiliary log term. So if you felt like it, you could make this log n times log n, but it'll actually give you worse space bound, so this is slightly better. Okay, then we apply step 3 prime, which is we look at each of the groups that we've identified, and either it's big and it has lots of 0 bits, or it's not big. And in either case, we're going to be happy. So if a group of log n squared 1 bits has r bits, we look at each of them individually. And if r is at least the square of that, so log n to the 4th power. So we're losing constants in the exponents, but it's not a big deal. Then store store all the answers, but now as relative indices. Okay, let's go over here. So how much do these relative indices cost? Again, it's at most order log n bits. To write them down. We don't know that a group is any smaller than log n, but it's at most the original size of log n. It's only log n bits to write each of them down. And now we get to say, oh, well, we had to write down log n squared 1 bits, but this could only happen n over log n to the 4th many times. So the space is n over log n to the 4th. That's the maximum number of these, I guess you call them sparse bit vectors. Sparse groups there could be, because each of them is at least this big. Total number of them is at most n divided by that. For each of them, we have to write down log n squared, different indices for our array, and each of those indices costs log n bits to write down. So this is log n to the third power, this is log n to the fourth power. So again, this is n over log n. You can tell I've tuned all of these numbers to come out to n over log n bits. Okay. That was the if case. There's the else case, which is that you have reduced to polylog size. Namely, then in the dense case, you have r is at most log n to the fourth. So at this point, so else you are further reduced. When you're further reduced, you have at most log n to the fourth bits, and at most log n squared of them are 1 bits, but we don't really care about that. Once we're down to a bit vector of polylog size, we can use our lookup table, and we're done. So that's select. If you want to do a select on an index, first you figure out which group it's in by dividing by log n, taking the floor. You teleport to the appropriate group using this array. Then within that group, there's a bit saying whether it was sparse or dense. If it was sparse, so lots of zeros in it, then you have a lookup table that gives you all your answers for the remainder of your query. If it's dense, then you go over here. You know that this thing will be stored, and so you figure out which subgroup you belong to by dividing by log n squared, taking the floor. There's an array, this thing, that teleports you to that group, to that subgroup, and then you apply, then there's a bit there saying whether it was sparse or dense. If it was sparse, there's a lookup table giving you the answer. If it was dense, there's an index into the number 1 lookup table that tells you what this bit string is, because there's only log n to the fourth bits. So just in fact, that is the index. Just what those bits are lets you look up into this table and solve your query in constant time. In all cases, constant time. But here's a little bit more branching, depending on the situation. Now, as I said, select is a little more complicated than rank, but in the end, constant time, little o of n space, n over log n, which can again be improved by Petrashku and n over log to the k, and for any constant k. Question?
Can you just quickly remind us how the 2 and 3 changed on the second recursion?
Okay, how did 2 and 3 change? You don't actually really need to change them. The big change is that you're storing only relative indices, not indices. So before, we're storing an array of indices of every log nth 1 bit. These were global pointers. But now, after 2 and 3, we've reduced to something of size log n or polylog n. We need to exploit that here so that we're only storing log n bits. If we didn't do that, this would be order n bits and then be too big. That's really the only thing you need to change. The other thing I changed was this value. If you follow that plan, it would be there's also a square. So we did have to add the square here. You could also add a log n term here, but it won't matter. Basically, you do something that works. The square was necessary to cancel out this guy, for example. You didn't do the square. Well, so instead of this, you could have done log n times log n without the square. Then here you would have gotten n over log n. So you could have followed the same pattern. You just get a slightly worse space bound. I tuned it here. Here we could not have afforded to go to log squared, if I recall correctly, though you can check that. Maybe it's a good PSET question. There's lots of choices that work here, but this is the one I find the cleanest that gets a decent bound. Not the best bound, but reasonable. Other questions? I think that's all that I changed. The sparsity definition was still a squared thing. So it was squared over here, and it was squared over here. It's just the thing we were squaring was a little different. Okay. One more thing I want to talk about. So at this point, we just finished this level order representation of binary tries. because we already saw left child, right child, and parent reduced to rank and select. We just solved rank and select in little o of n bits. So at least statically, we can do left child, right child, parent in a binary trie now in constant time per operation, 2n plus little o of n bits of space. The 2n bits are to store those 2n bits that we wrote down before. So that's succinct binary tries. Done. One mention, there are some dynamic versions. In particular, there are dynamic versions of rank and select, but the best versions that are known to do dynamic rank and select achieve something like log over log log time per operation, if you're interested in dynamic. So this is kind of annoying. If you want to go to dynamic, either you pay more time or you don't use rank and select. But I'm not going to worry too much about dynamic. Stick to rank and select. But there's one more thing on this list, which is a different way to do succinct binary tries. And this different way is going to be more powerful, more useful for things like suffix trees, which is what we're going to do next class. So I want to tell you a little bit about this. The level order representation is kind of like a warm-up. It motivates rank and select. But it does not let us do subtree size. Subtree size would be nice to do, because you care about how many matches you have after you do a search down a suffix tree. Level order just ain't going to cut it for that. So we're going to use different representation. We're still going to use rank and select a lot, and generalized forms of rank and select. But it's going to be a little bit more handy. Essentially, I want to do more like a depth-first search of the trie, less like a less level order, so more depth-first. Okay, here's our friend, the binary trie. Same one as before. We had our binary representation of it. I'm not going to draw that here. First thing I want to do is say, hey, look, this is the same thing as a rooted ordered tree. I already mentioned that there's the same number of them. There's Catalan of these, and there's Catalan of these. So a rooted ordered tree has a node, it has some number of children, and then more nodes. The children are ordered, but they don't have labels on them. So it's a tree, not a trie. Okay. So I claim these two things are equivalent, and there's a nice combinatorial bijection between them, which you may have seen before. It's kind of a classic, but here we're going to use it for handy stuff. Basically, so binary tries distinguish between left and right. Rooted ordered trees do not. They just have order. So to clean that up, I'm going to look at the right spine of the trie, distinguish that because right and left make a difference here, and then recurse. So this is the right spine of down here. This is the right spine of this subtree. Now every node lives in some right spine. And then I'm just going to rotate 45 degrees counterclockwise. So I have AEG. That's my first right spine. I'm going to think of them as children of a new root node. And then they have children below that which correspond to the right spines that hang below. So A, for example, has this right spine BCD. So we have BCD here. E has a right spine of F hanging off of it. G has no right spine hanging off of it. So you need to prove that this is a real bijection. Every binary trie can be so converted into a rooted ordered tree, and it's unique. So if it's different over here, it'll be different over here. And you can convert backwards as well if you just delete the superroot and turn all the children into a right spine or recurse. They're really the same thing. This is why there's Catalan of each of them. Okay. Now, what I'd really like to get to is balanced parentheses. And while it's a little unclear how to represent a binary trie with balanced parentheses, these things it's really clear how to represent a binary, represent with balanced parentheses. Here I just do an Euler tour, which was a depth first search, visiting these things. And every time I start a node, I'll write an open paren. Every time I finish a node, I write a closed paren. Similar to representation we talked about before. So this would be, I'm going to need more space. This is going to be an open paren for star. Why don't I make that one really big? We start here, then we open the A chunk, then we do B, which has no children, then we do C, which has no children, then we do D, which has no children, and that finishes A. Okay, then we start E, then we do F, then we finish F, we finish E, then we do G, and then we're done with star. Okay, so that's a very easy transformation. Again, there are Catalan many of these balanced parens. You think, oh, there's 2 to the n of them, because each paren could be open or closed, but they have to be balanced, so it's a little bit more constrained than that. And so it ends up being Catalan of n over 2 if there's n parens. Because there's 2 parens here for every node over here. This is going to be our bit string. Open parens are 0s, closed parens are 1s. This has roughly 2n bits, 2n plus 2, I guess, for the star, relative to this n. So basically, nodes here correspond to nodes here, which correspond to an open paren, closed paren pair over here. Now, we can't afford to store these labels. Those are just guidelines to think about what you need. So let's think about, there are 3 things we really want here: left child, right child, and parent. This is the thing that we care about, but this is what we're going to store. So I want to translate from here to here to here. This is an exercise in translation. So what does a left child mean here? Left child over here corresponds to, well, I guess it goes, in general, the left child goes to this branch, which is like all of these children pointers from A. But really, if you follow the left child, you get to B, not any of the other things on the right spine. You always get to the top of the right spine. Top of the right spine is the leftmost node in the spine here. In other words, it is the first child of a node. First child of a node, if there is one, is going to be the left child over here. Right child is like following the spine. That's like going this way. So right child is what I would call next sibling. The next sibling to the right. If there is one, that's going to correspond to the right child because we're just following a right spine. Okay, parent is a little trickier. Parent is the reverse of these. So either you take your previous sibling, but if you're here and there is no previous sibling, then you take your actual parent. Because the parent should walk up here. This is like going left, previous sibling, previous sibling. Parent of this guy, though, is the actual parent over here. So this is going to be previous sibling if there is one, or if there isn't one, you go to the parent. Okay, so that's the easy translation. Now we need to convert these pictures into balanced parentheses pictures, which is also going to be easy in itself, but the jump all the way from binary tries to balanced parens would be pretty confusing. So that's why we have this intermediate step. So we want first child here. If I have a paren, like look, I'm looking at A. So A corresponds to this paren and this paren. I'm going to represent the node, let's say, by the first paren. Then the first child is just the very next character. Right? You put the first child right after that open paren. So this is really the next character. If we want to find the first child, this is if it's an open paren. It could be the very next, like if you're doing B, the very next character is a closed paren. That means there are no children. Okay, but that's how you can tell whether there's a child. If there's an open paren right after your open paren, that's your next child. That's your first child, I should say. Now, what about next sibling? So let's say, again, I'm at A, and I want to know the next sibling. Next sibling is E. So that's like I go to the closed paren for A, and then I go to the next character. So this would be go to the closed paren for where you are right now, and then go to the next character. This is, again, if it's an open paren. If it's a closed paren, then you have no next sibling. So again, you can tell whether this operation fails. What we need is an operation given a bit string representing balanced parentheses, and given a query position of a left paren, I need to know what is the matching right paren. And I'll just wave my hands and claim that can be done with the same techniques as rank and select. It's not easy. It's quite a bit harder, but you do enough of these recursions, eventually you can solve it. Okay, last operation is parent over here, which corresponds to previous sibling, or parent over here, which corresponds to, there are two cases. We want to move backwards, so here we're always ending with next character. So the first thing we do is go to the previous character. And there are two cases. If it's a closed paren, so let's say we're here at E, we go to the previous character. If it's a closed paren, then A is our previous sibling. And so we want to do the previous sibling situation. We again find the match. We hit percent in VI, and what's the corresponding thing in Emacs? I forget. You go to the matching closed paren, open paren, and then there you go. You've got your previous sibling. So if it's a closed paren, then you go to the corresponding open paren. If the previous character is an open paren, then you're done. That's your parent. So like here, if you're at A, you go to the previous character and it's an open paren, then you just found the parent of A. There was no previous sibling. So in either case, you end up with an open paren corresponding to either your previous sibling or your parent. So that's left child, right child, parent. If you have this matching paren operation, you can do all of these in constant time, and little o of n space beyond the 2n bits to write down that bit string. That's not so exciting because we just reinvented the same results we had before of doing left, right, and parent in constant time. But what we buy out of this representation is we can now do subtree size. So this is a little bit trickier. Let me go to another board. But whereas with level representation it was impossible, now it is possible. And we're going to use subtree size, I think, next class when we do compact suffix trees. So subtree size is what we want in the binary trie. In the rooted order tree, it's a little tricky because subtrees no longer correspond to subtrees. For example, the subtree of C consists of this subtree and this subtree. So it's really C. Over here it's C and all of its right siblings. So this is size of the node plus size of right siblings, however many you have. Okay, so in the rooted order tree, it's actually kind of messy. Turns out in the balanced parenthesis, it's pretty clean because all your right siblings correspond to paren groups that just follow each other. And you want to know, so these are a bunch of siblings here, varying size. And we're given, say, this sibling. We want to know for this sibling up to all the ones to the right. So there's an enclosing parenthesis here for our parent in this representation. We want to know the length of these. So it's just we want to take here we are at this left paren. We want to compute the distance to the enclosing closed paren. So that's here. That's our enclosing closed paren. So here's a new operation. Given a paren pair, I want to compute the enclosing paren pair, these guys. That can also be done in constant time with rank and select-like techniques. And then you just measure this distance, and you divide by 2. That will give you the number of nodes in here. It's half the number of parens. That will give you subtree size. And we have a couple extra seconds. So another bonus is suppose you want to know the number of leaves in a subtree. If I recall correctly, that's something like, instead of doing this distance to the enclosing paren, you do something like rank of, so just rank of that. Those are the number of leaves of the enclosing closed paren. This is getting notationally confusing. Minus the rank of here. Okay, so I just want to compute how many open paren, closed parens are there from here to here. And so I just take the rank here, subtract by the rank here. That gives me the number of leaves in that range. So this is a generalization of rank. Before we did rank of just a single bit. This is rank of a 2-bit pattern. But 2 bits is not much harder than 1 bit. You can very easily adapt the rank structure we saw to do any 2-bit pattern instead of just the 1 bit. So that gives you the number of leaves in the subtree, which corresponds to the number of matches. So you can do lots of fun things like this. This representation is super powerful, and we'll use it next time.